Welcome to Hot Chips 30. Session 3, IoT and Edge Computing.
With that said, I'd like to introduce our first talk by Paul Whatmo from Harvard on a 16-nanometer neural network SoC. Paul?
Okay, so thanks for the introduction, Bill. It's my pleasure to be here today at Hot Chips. So I work for ARM Research, and I also have a part-time affiliation at Harvard. I'm going to be talking about a test chip we designed at Harvard recently called SMIV. And I'm also going to be talking more generally about accelerators for embedded devices. Okay, so the workload I'm going to be focusing on in this work is deep learning. So it's probably not a surprise, there's a huge amount of interest in deep learning at the moment. And this slide has two of the key sort of drivers for deep learning on embedded devices. So the first is making sense of sensor data. So by this, I mean using supervised learning to perform classification and regression problems in a diverse range of domains. So the graphic here kind of hints at some of the applications and use cases that we have in mind. And generally, deep learning is a really big enabler for a lot of these domains. And moving forwards, we're starting to think about things like multimodal data and even things like unsupervised learning, which can be really powerful in IoT. So the second thing I wanted to mention was next generation user interfaces. So I think this will be a really big driver for deep learning. The problem here is that these IoT devices typically have sort of very small form factors, and often they won't have a big screen or an input device, this kind of thing. So we need to start moving to new forms of user interfaces for these. And we're starting to see really convenient user interfaces that tend to be based around things like natural language. So we're using things like speech recognition and speech synthesis, gaze detection, even biometric authentication and things like that. So these are all driven by deep learning techniques these days, and we wouldn't be able to do these things without deep learning. Also, we're starting to be able to do things like personalize user interfaces and sort of predict user decision making. And kind of the new piece here in terms of SoC is that we really want to be able to, to do these DNN workloads locally on the edge device. At the moment, we currently offload to the cloud regularly where, we have more compute resources. But this sort of requires us to transmit our personal data, which sort of incurs problems with security and privacy and has latency and energy overheads. However, doing DNN inference locally on the edge device is pretty challenging, and we need a large compute and storage capability, and that's a real challenge on edge devices. So for DNN workloads, we usually have a pretty big performance gap compared to offloading. So how do we close this performance and energy efficiency gap on DNN workloads? So one thing we can do is to use more efficient networks. So here the idea is to try and design neural network architectures where we use less multiplications, which is basically the compute requirement, and we require less storage. So that's the number of parameters in the network. And in fact, there's been a lot of great work in this area. So one I'm going to point out is the Google Mobile Nets architecture. So this was an effort that was really successful in terms of reducing the compute and storage requirements for these workloads, but keeping a useful accuracy. On the hardware side, we can, of course, try and design more efficient hardware for these workloads. And there's lots of tricks we can use here, which have been pretty well studied over the last couple of years. So we can do things like reduce the precision of the data. We can move to 8-bit integers rather than floating point numbers. And we can exploit data reuse, which is especially useful for convolutional layers. We can compress the data. We can do things like fast convolution algorithms like Winograd. And we can also do things like sparse computation, so really driving down the amount of compute we have to do. And all these things are generally can be considered hardware specialization for neural network workloads. And I like to frame it in this way in terms of efficiency and flexibility. And this is kind of a sort of a metaphor that's been used quite a few times. I really like this. So the idea with architecture specialization is that we can design accelerators that are optimized for a certain workload. And this gives us improved power and performance at some kind of area overhead. And we still care a lot about silicon area in embedded devices. The extreme case of this is sort of a fixed function accelerator, which basically only does pretty much one thing, but does it really, really well in terms of performance and energy efficiency. However, the problem with this is that in certain fields like neural networks, the technology is moving forwards very quickly, so there's a big risk of premature obsolescence. So in terms of architecture terms, there's no real silver bullet here. We kind of need to map our workloads onto this scale and see what works. So the more sort of fluid workloads would suit more programmable architectures. And conversely, things which have converged quite well, perhaps such as image coding or video coding, it makes sense probably to design more fixed function hardware. There's another case for fixed function hardware in IoT devices where we spend a lot of our time in a very low power state where we're doing constant monitoring and always on monitoring. And in these cases, again, we're severely energy limited, so we probably want to design heavily optimized hardware. Okay, and then there's other interesting things from an architecture perspective like FPGA and coarse-grained reconfigurable architecture. So these map onto this scale in different ways depending on how they're implemented in the system. And talking of systems, I think this is a message that I like to stress. It's the system stupid. The thing that really counts is how good the achieved performance is overall. So we don't just care about accelerators in isolation. We care a lot about interfacing and memory systems for them. We care about abstractions and tools that allow us to map workloads in a useful way onto a heterogeneous SoC. A lot of stuff on this slide was the motivation for the work we did with SMIV at Harvard. So the idea is to have an SoC platform for architecture and systems research. Some details of the test chip here. So it's a relatively big chip. For academia, it's 25 millimeters square in a 16 nanometer TSMC process. It's more than 500 million transistors, nearly 10 megabytes of SRAM, 7 clock domains, 5 power domains. It's the first academic chip to feature an ARM Cortex-A class CPU. We have all digital gigahertz on-chip clock generation and chip-to-chip link, and a custom flip-chip BGA package. And this is an academic chip, so it's done in a very short design, validation, and implementation cycle. There's around 7 people worked on this design, including 4 PhDs and 3 postdocs. And the design from start to end was around 9 months, but the majority of the work was actually done in a much shorter timescale. In fact, the last RTL IP came in about 6 months before tape-out. Okay, so this is a simplified block diagram of the architecture. I'll quickly walk you through this design. So firstly, we have a near-threshold, always-on cluster. So the idea with this is most of the system will be powered down for as long as we can keep it powered down. And during that time, we have this always-on cluster running. This is designed to run at a very low supply voltage, so the power consumption is low, and we don't drain our battery. And when something interesting happens, so we can run sort of firmware for the system on this, and we can also do always-on monitoring, continuous monitoring. When something happens, we can send an interrupt to the CPU cluster. So we have dual Cortex-A53s in this chip. We have a 2 megabyte L2 cache. Connected to the CPU cluster, we have Cache-Coherent Datapath accelerators. So we have 4 of these. These were designed using high-level synthesis methodologies, and these connect to the CPU cluster via the accelerator coherency port on the CPU. We also have an embedded FPGA core from Flexlogix. So this is kind of a new thing for SoC, and that's connected to the SoC interconnect as a standalone accelerator, so the CPU can drive that and use that as it wishes. We also have 4 megabytes of SRAM on the SoC, and this is really important for the neural network workloads because they require lots of storage. And we also have an off-chip link to an FPGA board, which we use for our DRAM main memory and some other peripherals. So I'll quickly walk through those blocks in turn. So firstly, a near-threshold always-on cluster. So this consists of an ARM Cortex-M0 with some SRAM store, and it has some peripherals which we use to send interrupts to wake up the rest of the SoC. It also has sensor interfaces to do continuous monitoring. And it runs firmware for the system, and it performs sort of low-energy monitoring tasks, and it's heavily optimized for robust low-voltage operation, which is really important because we want to be using this regularly and we don't want to drain our battery. We also have an accelerator in there, so this is DNN engine classifier. So this is a second-generation design. First generation we published last year at ISSCC. And it's heavily optimized for fully connected neural networks, which are quite commonly used for small classification tasks. It also has 1 megabyte of SRAM, which is really important for these low-power designs because it means we don't have to use any off-chip memory access. It's very low power. In fact, the energy can be as low as 150 nanojoules per inference for small tasks like MNIST, handwritten digit classification. Okay, and then we have ARM Cortex-A53 CPU clusters. I won't say much about this. It's not actually the latest core in this line, but it's pretty representative of a vast majority of cores deployed in the wild. You probably have a few of these on the phone you have on you right now. It's a pretty efficient microarchitecture. It's an in-order pipeline with some limited dual issue. And one of the features that's on here that's been in ARM A-class CPUs for a while is the Accelerator Coherency port, or ACP. We actually use ACP in this design to connect accelerators. It's essentially a very efficient way to interface accelerators to the CPU so they can access memory coherently. It has very low hardware cost for the actual accelerator, and there's a number of advantages from having coherent access to memory. And because we reduce the cost of memory access in this way, it allows us to do an interesting thing, enabling a very fine-grained acceleration approach where we don't accelerate necessarily the whole workload, we focus on key kernels, which the CPU can then compose into that full workload. It also gives the accelerators access to the large L2 cache, which they can use as basically for more storage. And that mileage varies on that a little bit, so it works very well for networks that have lots of reuse, like convolutional layers. For other types of layer, like fully connected layers, there's no reuse in the weights typically, so we probably might choose to do uncached loads. Okay, so this is a simplified block diagram of the accelerators we attached via ACP. It's based around a unified SRAM buffer with dedicated data paths for fully connected convolution and reduction operations. And this design actually was modeled and implemented using high-level synthesis. Okay, and then we also have an embedded FPGA on this design. So this is from Flexlogix, so if you have questions specifically about this, I'd recommend you talk to them. I think they're here at the conference today. So this has a clever interconnect topology, which means they can actually achieve similar density and performance to a full custom FPGA, but using a standard cell approach. And in terms of the IP, it's scalable and flexible in terms of the array size and the layout. There's 2 basic building blocks. There's a logic tile, which has about 2,500 6-input LUTs and 21 kilobits of distributed memory. And then there's a DSP tile which has 40 wide hardware max and 1,800 6-input LUTs. So on SMIV, we actually have a 2x2 array, so we have 2 logic tiles and 2 DSP tiles. This gives us about 9,000 6-input lookup tables of logic and about 80 hardware max and 44 kilobits of RAM. And there's various use cases for embedded FPGA and SoC products because quite often we'd like to be able to reconfigure things post-silicon. But the approach we took, and we're particularly interested in with this, was to use the embedded FPGA as a standalone accelerator, which can be reconfigured. So it's a really interesting point for us on the efficiency versus flexibility sort of scale. Okay, so we have chips back from TSMC. There's a photograph here of our sort of test setup in the lab. The board on the bottom is the actual SMIV test board with the chip inside the black socket. On the top is a Xilinx FPGA board, so we use this for to provide a memory system with DRAM and also some other interfacing. And our initial bring-up was successful, all our pre-silicon tests passing on the first silicon. We have the off-chip interface to FPGA working when providing DRAM main memory. And we're able to program the FPGA, and it's fully functional. And so we're actively using SMIV now for our research program, and we're really trying to address a lot of the questions that I showed earlier in the motivation around what types of accelerators work well for neural network workloads. One thing we measured quite early on, which I wanted to share here, was we're really interested in comparing the 4 compute mechanisms we have on this chip. So the measurements shown here are for sort of representative DNN kernels. And we wanted to look at energy efficiency and area efficiency. So these are for CPU and the quad Datapath accelerators and the embedded FPGA and the fixed function always-on accelerator. And it's actually pretty difficult to compare these things in a sort of truly fair way. There's lots of small differences that make this hard, such as the bit widths, the data, and all these kinds of things, which do vary. But nonetheless, I think these trends kind of do give you a feel for what can be achieved with these accelerators. So starting with energy efficiency at the top, we see a range of about 10x from the ARM CPUs all the way up to the fixed function hardware accelerators. And this also spans the whole spectrum in terms of flexibility. So the fixed function always-on accelerator is very difficult to benefit from new algorithm advances in the field, although in some cases it may be, if it's possible to design better neural networks using less parameters, then that may be something we can still take advantage of. Okay, and then the area efficiency is kind of even harder to quantify and compare fairly, I think. It's pretty heavily impacted by the amount of SRAM in the design, and it's quite hard to sort of slice these things up. But it does sort of emphasize that it's pretty important to kind of share on-chip SRAM resources as best we can. And again, especially embedded where the cost of silicon area is very high. And again, ACP is really interesting in that regard because it allows accelerators to use large SRAM resources like L2 caches. Here we found embedded FPGA has an area overhead for reconfiguration. I think that comes out in the area efficiency plot. However, these numbers were mainly take into account the hardware max in the embedded FPGA, so it doesn't fairly account for the lookup table logic. Okay, so we designed this chip under a DARPA program called Circuit Realization at Faster Timescales, or CRAFT. And the sort of goal of this project was to sort of try and study how we can achieve high-quality SoC designs more quickly. As I said in the introduction, this was a pretty small team for this project, about 7 people. And the majority of the work was done in a pretty short timescale. So how did we make such a complex SoC in that short timescale? Well, I think there's a few things that I wanted to mention. Firstly, in terms of the IP we use for the SoC, so we used a mix of third-party IP and our own work. But we tried to stick where possible to sort of common industry strength, interfacing standards, and software ecosystem. And I think that's really important to try and avoid reinventing the wheel every day. We also used, in terms of tooling, we used a tool from ARM called Socrates, which is really great for SoC integration and IP configuration. We also reused some tooling and methodologies from previous chips at Harvard. So we have scripted methodologies for generating things like memory mapped registers, I/O pad rings, clock domains, all these kinds of things, pretty standard in industry. And then one interesting methodology choice is we didn't use any custom transistor layout at all. We used only standard cells and SRAMs, and that includes things like clock generation and off-chip link PHYs is usually done with custom layout. I think that saves a significant amount of time in terms of DRC and LVS and that kind of thing. Finally, again, under the CRAFT program, we used high-level synthesis to design our Datapath accelerators. And we actually used a methodology that Nvidia Research developed, who were on the same project for that. And then I guess my final remark on sort of rapid SoC design and implementation is that in industry, we have a very long tail of validation and timing closure. And that's generally to meet some kind of marketing specification, basically. In research, we always have this problem of not enough time and not enough people. And I think the compromise we can make is to be very clear about what our goals are in terms of validation quality. So we don't necessarily have to validate to 0 bugs, but we need to understand what we want to try and run when the silicon comes back. So we're very grateful for ARM for letting us use pretty representative CPUs in this chip. So I did want to briefly mention some of the research enablement offerings that ARM have. So the first one is Design Start. So this is a web portal. It allows you to get hold of ARM IP and example systems and software and documentation. So this is a really great resource. I recommend you check this out. We also starting to put a lot of effort into Gen 5 as a system tool. So this allows us to sort of provide things like CPU models. And if you're working on CPU modeling and system modeling and things like that, I recommend you check this out. And finally, if you're developing chips and research, we can also provide IP building blocks. So design IP, like CPUs, interconnects, peripherals, that kind of thing. And physical IP as well, of course. So if you're doing some work in that area, please do get in touch with the research enablement guys, and they'll try and get you what you need. Okay, so a quick summary. I talked about deep learning on edge devices. So this is driving new IoT use cases and applications. We're really interested in optimal solutions around efficient and flexible DNN acceleration. And we care a lot about system things like accelerator integration and memory systems. I described SMIV, which is a 16-nanometer SoC platform for architecture and systems research. And I spoke briefly about rapid SoC design and implementation. And then finally, I would like to acknowledge the sort of dedicated team at Harvard. This is a pretty big project, so I'd like to acknowledge all the hard work that went into it. And also to say thanks to our sponsors, including the DARPA Perfect and CRAFT programs, and to ARM, Flexlogix, and TSMC for IP support. And that's a lot. Happy to take questions.
Okay, thank you, Paul. If you have questions, please come up to the mics on either side. Okay, on the left, say who you are and ask your question.
My name's Engling, Goki US Lab. I was wondering if you might be able to elaborate on what kind of acceleration do you put onto the Flexlogix?
Yeah, sure. So far we've been, the results I showed there are for a fairly basic systolic array design for doing matrix multiplication. So that's probably reminiscent of something like a very small version of the Google TPU. So that's good for convolutional neural network layers. We're actually really interested in having embedded FPGA on an SoC because there's many other applications such as smart DMA engines, compressing DMA engines, and other SoC system type things we'd like to explore using sort of embedded FPGA.
But for the latter part of your answer, would the 2x2 FPGA suffice, or do you see that?
It depends what you're doing. So we had 2 DSP tiles and 2 logic tiles. The DSP tiles have 40 hardware multipliers each. So that gives you 80 max. So that gives you a fair amount of acceleration, yeah.
Okay, thank you. Are there any other questions? Now let's thank Paul again. Oh, if you have a question, go to the mic. Go to the mic.
It's protocol.
Hi, this is Hetulia from Texas Instruments.
Hey.
One question, why is the energy efficiency of the dedicated neural networks accelerator, the quad accelerator, poor as compared to the FPGA logic?
Yeah, so the dedicated accelerators we designed using HLS, and the main focus was on the interfacing for that. So the performance of them was actually fairly moderate. But those designs can be scaled up pretty strongly in terms of the accelerator design themselves.
Okay, all right, thank you.
Okay, well, thank you very much. Let's thank Paul once more. And the second talk in our session is from Vivienne Z's group at MIT, and it's on Navion, a chip for visual odometry.
Okay, thanks for the introduction, Bill. Where's the... Yeah, so today I'll be talking about our work, Navion, which is an energy-efficient visual-inertial odometry accelerator for micro-robotics and beyond. Before I start, I want to acknowledge my collaborators. So this work was primarily done by my 2 students, Suleiman and Zhengdong Zhang, and in collaboration with Luca, Carlone, and Sertac Karaman in the Aero-Astro department at MIT. So we know that autonomous navigation is becoming increasingly important. Already there's many self-driving cars being tested on today's roads. We know that some companies are looking into having autonomous UAVs or drones deliver packages directly to homes. And also, if you've gone to malls recently, you might have seen some robots being used in the parking lots. And back in Boston, we have Boston Dynamics that's building these 4-legged robots that can run autonomously. And these robots continue to shrink. In terms of shrinking robots, one of the focuses of our research is looking at miniaturized robots. And what we mean by this is that the form factors are actually very small. So in terms of drones, we're talking about micro robots that are basically handheld all the way down to pico-scaled robots that are the size of a penny. And these robots are very useful for a wide range of applications, in particular navigating unknown environments that are very heavily constrained. So for example, during a large disaster, if there's a search and rescue mission in a collapsed building, the size of these robots make them very amenable to moving through very small constrained areas. You can also imagine they're useful for applications like surveillance as well. However, there is a challenge to make these robots autonomous. So let's first go through what are the key steps in autonomous navigation. So there's 3 key blocks. The first is perception. So the main importance of perception is that it determines where you actually are in an environment, particularly an unknown environment itself. So it allows you to recognize your environments, recognize important objects within the environments, and then locate yourself. Once you know where you actually are as a robot, the next step is to plan the motion in terms of determine where you want to go next. And so that involves motion planning. And then finally, you'll have controls, which basically send the control signals to the actuators to move the robot to that particular location. Out of all 3 of these computation engines, the perception aspect tends to dominate in terms of the computation bottleneck. And I'll explain why computation tends to dominate. So the first aspect is that typically in the perception aspect, we have to deal with high dimensional data. So in particular, in perception, we're receiving a lot of the data from the sensors itself. So in this particular case, we're looking at visual data. So you can imagine the resolution of these visual images dictate how far we can actually see, so they tend to be higher resolution. And then the frame rate at which we're receiving these images dictate how quickly the robot can go, because effectively the frame rate is sampling our environment. So the faster you want to go, then the faster the frame rate you need to support. But in addition to this very high dimensional data that kind of streams into the chip that you have to process, also in order to see, for example, objects of different sizes, you need to expand this data. So for example, image pyramids are very commonly used in vision applications to detect objects of different scales. In addition to this, if we're doing a mapping operation, this map tends to grow in size over time, and we also have to handle this high dimensional data of the map itself. Another challenge, particularly when we talk about these micro robots, is that we need to fit all of this processing on a very small platform. The small platform means that we have very limited battery capacity because we can't have a very large battery. And that also means that we have limitations in terms of how much compute we can actually do on this platform. So even conventional CPUs and GPUs just won't cut it in terms of their energy consumption. So giving you one particular example, if we look at an insect-sized drone or UAV, it would cost around 100 milliwatts to lift this drone. If we're talking about sensing, for example, using cameras, we're talking about another 100 milliwatts. But if we use the conventional CPUs and GPUs and even embedded CPUs and GPUs, you're talking about 10 to 100 watts, which is much higher than the other two aspects or components in terms of the power consumption of the system. So it's really important for us to address the computational challenges of this particular robot itself. So in today's talk, I'm going to discuss our work, Navion, which is an energy-efficient visual-inertial odometry accelerator. The main function of this is that it achieves energy-efficient, real-time localization and mapping. So for real-time performance of 20 frames per second, it can perform that at 2 milliwatts. And then if we look at peak performance, where we can go all the way up to 171 frames per second, we're consuming an average of 24 milliwatts. So in today's talk, I'm going to try and cover all 5 of these aspects. I'll first give an overview of the algorithm itself. Then we'll describe the high-level chip architecture, highlight some of the contributions that we did in order to accelerate the design itself. I won't be able to cover all the design aspects, but I'll give you some highlights, and then discuss the chip specifications, and compare it to various different platforms, and then summarize the results in the conclusion of this talk. So let's first walk through the key algorithm of visual-inertial odometry that we use for localization and mapping. So the key idea here is that we take in visual data, so an image sequence from a camera that's mounted on the drone, as well as an IMU, or initial measurement unit, that's also mounted on the drone. And we take the input from these two sensors, and we fuse it, and through these sensors, we detect 2 important things. We generate 2 important things. One is localization. So you can see here on the upper right-hand corner, what we're showing is that with the visual data coming in, we're able to estimate the state of the robot itself, particularly both the pose, so which direction the robot is looking at, and also its location within a 3D space. And then the combination of all of these states over time is the trajectory of the robot itself. So you can see a trajectory in the 3D space. Because we're also trying to navigate an unknown environment, we also need to map the environment itself. So that's the other output shown at the bottom right-hand side of the visual-inertial odometry. Now, VIO is a subset of the SLAM algorithm. So SLAM stands for simultaneous localization and mapping. And you may be familiar with that algorithm because it's widely used in the robotics community for localization and mapping. So basically what VIO is a subset of SLAM. It's basically SLAM without without loop closure. And this is because loop closure is typically done at a lower frequency. And so as a result, it can be done offline. So let's walk through the key stages of VIO. In particular, there's 2 actual stages. So we'll first talk about the front end, which is typically used to process the visual or the sensor data that's coming in. So we'll talk about the vision front end first. So it takes in both a stereo input from the camera itself, and it can process the stereo input as both stereo or mono images. In particular, what it's actually trying to do is it's trying to track various landmarks in the environment itself. So you can see from our example here, we have various feature tracks that is tracking. These 3D landmarks in the environment appear as 2D features in these actual images, and we want to track them across the different frames or across time. And by tracking these particular features, it gives us a sense of which direction and where the drone is actually looking. So for example, if you follow the red line here showing landmark number 2, you can see that its position within the different frames will vary, and you can get an idea of where the robot is actually moving based on this location. Now, we perform this tracking on all the frames, but then between or at each subset or a keyframe, we basically want to summarize the tracks, and with this particular algorithm, it's going to output the tracks across the different keyframes, which is a subset of the total frames, though we are performing tracking on every single frame itself. And the composition of these feature tracks is basically the keyframe ID, indicating which frame contains this landmark, as well as the feature coordinates, indicating the location of the landmark within the frame itself. The second vision front end, or second front end component that we have is the IMU front end, and this takes in measurements from the IMU itself, specifically measurements from the gyroscope and accelerometer. You can see here at the bottom of that it happens at a very high rate. And so what we do is we perform pre-integration to basically summarize the state estimates based on the gyro and accelerometer per keyframe. So we perform this pre-integration and try to estimate how the state of the drone has changed between each of the keyframes. And just to remind you, what we mean here by state is the pose or the rotation of the drone itself, and then the location or translation of the drone itself. Once we have these two inputs, we send them to the back end, where they're actually fused together for processing. Primarily, the role of the back end is twofold. One is that when we do the IMU processing, there is some bias in the IMU that changes over time, and it creates some error. And so the goal of the back end is to fuse it with the visual data to overcome this error itself. The second thing that we want to do on the back end is that we want to update the state to by minimizing the inconsistencies between the different measurements over time. So can you imagine in the visual data, as you look at an object from different perspectives, there might be some misalignment in terms of the data. So you want to optimize and avoid and reduce these inconsistencies. So the way that this backend does this is that it formulates the problem as what we call a factor graph. So let's first look here at the bottom in terms of what the factor graph is. So shown here in the blue is the states of the drone itself over time. And you can see, for example, the landmarks in green show the relationship between the different states of the drone itself over time. So the green would be the vision factors. And then similarly, we have IMU factors that, again, show the relationship between the different states. So the overall goal is to take these factors and we basically fit it into the constraints of this optimization problem. We solve it as a nonlinear least square factor graph optimization. The other thing I want to mention is we perform this optimization over a range of keyframes, which we refer to as the horizon. So we're not just looking at one measurement or one timestamp, but we do the optimization across multiple timestamps or multiple keyframes. So as a result, the size of the factor graph can be quite large. We're talking about over 4,000 factors. And then furthermore, the factor graph itself changes over time. So it's dynamically changing based on the data that it's collecting. Once we can solve this factor graph and we have the updated states, as we generate the updated states every keyframe, as well as a sparse 3D map. Let's talk briefly about the chip architecture itself. So shown here is an image of the chip architecture. We can see here on the left-hand side is the vision front end, on the bottom side is the IMU front end, and at the top is the back end itself. So one of the key challenges or key goals of our work is that we want to fully integrate all these different components onto the chip itself, because we want to avoid costly off-chip storage and off-chip processing, because it increases the overall energy of the system as well as the overall cost. So imagine if you want to put this on a small drone, you want to minimize the number of off-chip components. I'll just quickly highlight some of the key properties of each of these particular modules. So for the visual front end, it's doing all the image processing. It uses fixed point arithmetic, and because it's doing image processing, it can exploit parallels and pipelining. Again, it can process both mono and stereo camera images, and it typically operates at the sensor rate. So in this particular case, we can operate all the way up to 171 frames per second. After it does all this processing of the image that's coming in, it then generates a feature tracks at the keyframe rate. The other actual module that we have is the IMU front end, which performs pre-integration. Here, we're operating at double precision arithmetic. It's actually quite low cost. It's only about 2.4% of the total area and 1.2% of the overall power. Again, we're operating at the sensor rate here, so it can operate up to 52 kilohertz. And here, it's generating an estimated state every keyframe again. And then finally, you have the backend that solves that very large optimization problem to fuse both the visual data as well as the IMU data. Now, the backend also needs to run at double precision, because in order to properly solve the actual optimization problem, we need to have this type of precision to prevent the problem from being ill-posed. It is basically an implementation of a very complex and large finite state machine, which you can see here we break into smaller finite state machines, and then it operates at the key frame rate, in this particular case, up to about 90 frames per second. And here we're updating, or the output of the backend is going to be the updated states as well as the 3D map. Some additional challenges for this full integration. So we might have noticed in the image that we have lots of components. In particular, in the vision front end, it contains many heterogeneous computation modules. So we have first feature detection, detect the important features in the image. Then you need to do feature tracking, because we need to know the 3D location of these particular tracks. We also have to do stereo matching for disparity calculations. And then in both the feature tracking and stereo matching, there tends to be outliers. So we need to perform ransack to reject these outliers. And there's a few other modules as well. So it's quite complicated to integrate all of these different modules onto the same system. On the backend itself, as we mentioned, it solves a very high-dimensional, complex factor graph optimization. There are over 4,000 factors within this factor graph itself. Again, it's dynamically changing over time. And we need to keep the high precision in order to do in order to properly solve this factor graph optimization. All right, so what are some of the highlights or key contributions to this work where we can actually optimize this design itself? So again, here we're just showing here for completeness the full system. And when we want to integrate the full system, one thing that tends to be challenging is the cost of the memory itself. We know that memory tends to dominate both area and power consumption, so this is something we really want to address in this work. So in particular, the memories that we're going to discuss today are the frame buffers used for both the tracking and the stereo, which consume or account for about 1.4 megs. We have the graph memory, particularly the feature tracks, and those account for about 962 kilobytes. And then we have the linear solver memory, which is around 700 kilobytes. And then the key strategy we're going to take here is going to leverage compression and sparsity. So let's first talk about compression. In particular, we're going to apply this to the frame buffer memories themselves. Remember, we had 4 of them. We're going to apply lossy block-wise image compression. And so what that actually means is we're going to break the image down into 4x4 blocks of pixels. For each of these 4x4 blocks of pixels, we're going to find the minimum and maximum value, which will allow us to determine the dynamic range. From the minimum and maximum value, we'll determine what the middle threshold will be. And then what we do is for each of the pixels within this 4x4 block, we're going to compare it to that threshold. And then as a result, either the value is above or below this threshold, so then we can represent each pixel with 1 bit per pixel. On the decoder side, what we receive is this value of 1 or above or below 1 bit per pixel, as well as the minimum value and the threshold, and then we can reconstruct this 4x4 block of pixels. And so you can see this is a lossy, a particular approach, but here, as a result of this compression, rather than using 8 bits per pixel, now we only need 1.6 bits per pixel, and all in all, we have a 4.4x memory reduction size. Here we only apply this compression on the feature tracks and sparse stereo matching because this has the least impact in terms of accuracy. We do not actually apply it to detection because the impact on accuracy would be much larger. The second thing that we want to exploit is sparsity, in particular both structured and unstructured sparsity. So let's start with the structured sparsity itself. So when we look at the linear solver memory, in particular, when we're looking at solving that very large nonlinear optimization, we can actually solve that nonlinear optimization by linearizing it into a large linear system of equations. So shown here is the Hessian matrix, H times the state update delta equals epsilon. We want to solve this equation. And I've shown here on the left-hand side the Hessian matrix itself, which is 300 by 300. The size of this matrix is dictated by the size of the horizon. So how many frames are we optimizing across at a given time, or how many keyframes in particular. There are some important properties that we can leverage here. So this Hessian matrix is symmetric, so that cuts the memory requirements down by half. And then furthermore, as you'll notice, it's also quite sparse. So the black blocks here show the non-zero values, so we can see that majority of the values within the Hessian matrix are 0. So again, we can exploit that for further savings in terms of storage costs. In addition, while we're actually processing this data, we can also exploit this for higher speeds. So we can get about a 7.2x speed up by only processing the non-zero values. So in summary, we're getting about a 5.2x memory size reduction by exploiting sparsity, and then we're getting a 7.2x speed up by skipping the processing of zeros. Next, we're going to talk about the unstructured sparsity that we have due to the feature tracks. This is both unstructured and dynamic sparsity, so it's changing over time. So feature tracks actually account for 80% of the graph memory. So again, feature tracks are those vision vectors that are constraining the states of the different keyframes. Just again to remind you, in these particular feature tracks, you can see that the length of the feature track will vary. So some of them go across all the keyframes, some of them do not, because sometimes the landmarks fall outside the view of the camera. So it really depends on the movement of the camera itself. So the lengths of the feature track vary, as well as the number of feature tracks and the starting and ending points of the feature track also vary. If you want to store all these feature tracks in one particular memory, one memory itself, in the worst case, you need a very large memory, which is almost 1 megabyte of memory itself. But if you look closer at the problem, you'll realize that there's only around 200 by 20, so 4,000 unique points that are ever being captured at a given period of time. So we can actually break this memory down into 2 stages. So the first stage is storing the keyframe ID, which is 5 bits, as well as a pointer, and this can be actually quite sparse. And then the second stage is going to be storing the expensive 3D points that are 64 bits each. But in this expensive values, these are stored in a dense format, so it's much smaller in size. And so as a result, by taking this 2-stage approach, we get a 5.4x memory size reduction, and the extra overhead of doing this is this 1 extra cycle of latency. All right, so what does this all get us? Let's take a look at the chip itself. So this is the Navion chip. It was fabricated in a 65 nanometer LP process in CMOS. The chip area size is 4 millimeters by 5 millimeters, so 20 square millimeter itself. In terms of the logic gates, in terms of Nantude gates, it's about 2 million gates. The resolution that it supports is going to be 752 by 480, and we'll explain why we target that soon next. And then overall, the amount of on-chip memory we have, based on all of those particular optimizations, is around 854 kbytes. The one thing I also want to highlight in this particular chip is that we have over 250 parameters that can be used to configure the chip so that it can adapt to any sensor input as well as any environments. And we'll soon see how the environments actually help in terms of energy efficiency. So in order to evaluate this chip, so one quick thing. So if we look at the overall optimizations that we just highlighted in terms of the memory optimizations, we get in total about a 4.2x reduction in the overall memory size. So let's talk about how do we actually evaluate this chip. So we actually use the UROC dataset, which is a very challenging and widely used UAV dataset in the robotics community. It consists of 11 sequences with 3 categories: easy, medium, and difficult. So you can see at the top row the easy sequences, where basically the drone is moving quite slowly, and you can see that the features are pretty well defined. Whereas if you look at the bottom row, which is the difficult sequences, you can have very dark scenes, and you can have a lot of motion blur if the drone is moving very quickly. The inputs of this UROC data set is basically that 752 by 480, which is why we size the input of our chip like that. So what are some of the performance values for our chip? So at peak performance, so when we're running at the maximum frequency with the maximum configuration, so the largest number of keyframes, the largest number of features to be tracked, and so on, we can run the visual front end. So basically, this is the camera rate at between 28 to 171 frames per second, or 71 frames per second on average. And then the back end, which is the keyframe rate, this is the rate at which we update the state of the drone. We run between 16 to 90 frames per second, so for an average of about 19 frames per second. And the power consumption is 24 milliwatts. And then the trajectory error, which basically measures the error of the drone based on the ground truth compared to how far it's actually flown, which is around 0.28%. Now, if we configure the chip to perform in real time, and the definition here of real time is at the camera rate at which the video is captured, which is 20 frames per second, and having a back-end update at 5 frames per second. And then we also optimize those configuration parameters, in particular, things like the horizon, so the number of keyframes we bring into the optimization, the number of features that we're actually tracking. If we bring those all together and we optimize them for the different environments, we can actually significantly drop the power consumption down to about 2 milliwatts, and still we're able to maintain the trajectory error of around 0.27%. Now let's compare it to some other platforms, so particularly a server-scale Xeon CPU and then an ARM Cortex-A53 processor. You'll see here that the trajectory area of Navion is slightly higher than the Xeon and ARM processor implementations. This is due to the fact that we used fixed point in the front end, and we used image compression as well. But I should note that most of the state-of-the-art VIO algorithms have trajectory errors of around 0.5% or below, so we're still well within that range. In terms of camera rate, you can see that Navion tends to perform at higher frames per second than those particular software implementations. Similarly, with keyframe rates, Navion performs higher. And then in terms of average power, Navion is between 24 milliwatts at its peak and then 2 milliwatts when it's operating at real time. So if we look at the energy consumed per update, per keyframe update, we can see that Navion is operating in its optimal case at 0.7 millijoules per keyframe, and at its peak performance around 2.3 millijoules per keyframe. So this adds up to about 3 to 4 orders of magnitude higher energy efficiency than processing it on an ARM CPU or an Intel server-level processor. One thing I want to highlight is that we actually, I don't know if it's going to. Can you guys help play the video? So this is a demo itself of the, I guess this doesn't work. This is the video itself, since I don't have an ability to click on here right now, but this is the demo video. And what we're showing here, and you can go to YouTube to see it, even though I can't play it here, is that taking in the video at real time, it can figure out what the 3D trajectory actually is. The demo consists of both the chip itself and its interface to an FPGA, which allows it to take the inputs and generate the outputs. So I encourage you to go take a look on YouTube to play it. Or, yeah, how do you play it? Oh, okay. Extended screen. All right. But now I gave away the ending. So now you guys know what it's actually doing. So here's the 3D trajectory that's processing. Here's the actual demo setup with the FPGA and the chip itself. You can see the power consumption's around 10 milliwatts and below, and then you can see it's plotting the trajectory in real time. And this is just displaying the keyframes. So if you looked at the actual frames that it's tracking, it would be much faster itself. So just to summarize, here we're presenting the first fully integrated VIO pipeline on chip for robotic perception. We leverage compression and sparsity to reduce the memory size itself. We're talking about a 4.4x reduction in image compression, a 5.2x reduction using structured sparsity in the linear solver, and then a 5.4x by exploiting unstructured sparsity with the feature tracks. Navion gives 2 to 3 orders of magnitude more energy efficient than CPU implementations. And we also want to acknowledge our sponsors, which is Air Force, the Office of Air Force Scientific Research, and NSF. If you want to know more about Navion, this is just as I mentioned, there are several other optimizations that we've done that we weren't able to fit in today's presentation. I encourage you to visit the project website. We have a paper from VLSI just this past year, and then a paper discussing both the joint algorithm hardware design optimization at RSS last year. So one other thing to note, so Navion really focused on looking at the geometric understanding of the sensors that come in. Another important part of drone navigation is also to get a semantic understanding of your environment, meaning doing things like object detection and so on. I just want to highlight 2 pieces of work from our group that also address this. One in particular is an object detection chip that we published in 2015, and in this particular chip, we're able to do object detection with energy that's less than video compression. The reason why we compare it to video compression is that that's a typical default, that you would compress the video and send it up. But for that same energy, so below 1 nanojoule per pixel, we're able to do object detection at HD 30 frames per second. And then some other work that we've done in the deep learning space is looking at Iris. One particular, which we published in 2016, one particular challenge that we're looking at the second version of Iris is to support flexibility. So we heard from the previous talk that one of the challenges is that these neural nets, the dimensions of the neural nets continue to evolve. And so it's really important to have flexibility so that you can still be efficient across a wide range of neural nets, even compact neural nets like mobile nets, which only, let's say, have one particular channel for a given time. So you really want to have flexibility, and that's the focus of Iris V2. So I would encourage you to also check that out if you're interested in that topic. So that summarizes my talk. Thank you very much.
Well, thank you, Vivienne. If you have questions, please come up to one of the microphones on either side. Well, I'll kick things off with a question. So why do you need 64-bit floating point to represent a point in these sort of 500 by 700 images?
Great, thank you very much. So it's actually the floating point comes only in the optimization aspect of the system. In the front end, we're still using fixed point. In the back end, we actually have to use floating point because otherwise the problem tends to be ill-posed, and then we can't actually, the solver doesn't actually solve the system itself. It just basically, you would get a not a number type of effect. So we did try to reduce that, but when you deal with optimizations, you need that precision. Thank you.
Thank you. So we have a question on the right.
Yeah, Scott Johnson from Google. Question, do you require the landmarks to get that level of accuracy?
So do we require?
Landmarks that you're using the keyframe notations on?
To get what? To get which accuracy? To get
accuracy that you're getting to.
Yeah, so you do need, so what we do is we detect up to 200 features per frame, and we detect and track up to 200 features per frame. So you need to have landmarks. So if there's no landmark, right now we're using visual data. If you don't have any landmarks, then you actually have to rely entirely on your IMU. And so there will be some drift with the bias there. Is that the question? If you have a...
One of your first slides, you talked about some of the applications being like in disaster scenarios where you're going into dark places. I assume that you would have some drift in those cases? Yes,
you would have some drift. So the idea is that you would have the IMU there that would help you, but then your error would go up, right, if you don't have visual data to correct for that.
If there are no other questions, let's thank Vivienne again. And so our final talk of the session will be presented by Michael Ditty of Nvidia, and it's on Nvidia's Xavier SoC.
Hi, so my name is Mike Ditty. I'm the lead architect for the Xavier SoC. And so I wanted to just tell you guys a little today about how we built it and why. So as we started to look at what our next SoC needed to be, there's this booming era of sort of autonomy. Deep learning has made it easier to design algorithms for autonomous machines, robots, and compute has become more and more readily accessible to make it easier to put together algorithms. And so we looked at what do we need in an autonomous machine chip. And with DL, we looked at it. We need tens of deep learning teraops. And then we looked at compute. And again, you want tens of people are doing different things in computer vision, as we just heard. You want in some of these high-end systems, you want tens of tops of computer vision and compute performance. And so we started to look at how can I build a chip that can fit in these markets, but still be efficient, still meet the power targets that some of these may have. And so we knew we needed to design some new things. And so Xavier innovations, what did we create? So first we needed a CPU. We needed a CPU that had safety built in, had high performance. We included in Xavier our NVIDIA designed Carmel ARM CPU. We also needed a GPU. Now we have one of those, that's easy. But we did need to look at how we could improve it for these sort of inference workloads. And so we'll talk about that. The next thing we needed is, we know that we have this very great GPU. It's very powerful, programmable, but we know that there's certain things where if we know exactly what we need to do, we can build fixed function accelerators, as we've heard from today, and we can build a deep learning accelerator that for some key use cases and limited programmability, we can excel. And so we looked at how can we build a deep learning accelerator to augment the capabilities of the GPU, and also provide some diversity of hardware. As we look at safety systems, it's good to have diversity of hardware to run different algorithms on or run algorithms differently depending on your safety requirements. So next we looked at all these computer vision workloads. The GPU is very good at a lot of them, but we can build some custom hardware that is extra efficient at certain aspects of it. And so we built a programmable vision accelerator. We call it the PVA, and we'll talk about that some more. And then we looked at our ISP. Now, our Tegra SoCs have had an ISP focused on mobile and your smartphones, your tablets. But we knew that in the era of HDR sensors and these different environments, we were going to need to enhance the ISP. And so we re-architected the ISP, added native HDR support, higher precision math, so we could keep that data around, keep the dynamic range, and be efficient and not have to go to the GPU for that sort of really understood computer vision sensor processing. And then we looked at a number of other accelerators. Stereo and optical flow are aspects of a number of vision algorithms, as we just heard. And so we looked at, hey, what do we need to add to our multimedia accelerators? You know, we of course have video and all those, but from a machine learning and autonomous vehicle, what do we need to add? So all of those things are great. You know, 6 different kinds of accelerators. We also needed to build a system that had the right base to support all that. So high-speed I/O. We added the next generation of high-speed I/O. We have over 40 gigabytes of bandwidth. We knew that we needed safety. These autonomous vehicles need to have safety, and that needs to come from the start of development. So we looked at our development processes to make sure that they're meeting the ISO 26262 standard for sort of systematic design. And then we also looked at the hardware, and we added ECC parity throughout RAMs and buses, and some places redundancy. And so that's a very important base of the system to be functional in these different environments. Every system needs security. We looked at enhancing the security, both the system security of buses and bridges and topologies, also crypto standards and things. So Xavier has a base of security improvements from the last generation. And then we needed to optimize for energy efficiency. So many of these units we designed, chose process and transistor choices using TSMC's 12 FFN and our own recipes to meet an energy efficiency goal. And so that means it's going to be optimized differently than, let's say, a desktop GPU. So all that put together, around 4 years ago, we started all these discussions. I think I was here talking at Hot Chips about Tegra K1 4 years ago. And so now we're here. This is our chip. It's one of the most complex SoCs ever made. Unlike our big GPUs, we have tons of individual units here, many individual customized layouts, not big blocks replicated. So 350 millimeters squared, and over 8,000 engineering years went into it. So tons of work, a lot of people, software, hardware, architecture, across the board. And we're very proud of it. So let's talk about it some more. So our Carmel CPU. Our Carmel CPU cluster, we have 8 cores. These are ARM v8.2, and we include ARM's RAS support, so we've built our safety, reliability around the ARM standard for RAS. The clusters are made up of 2 cores each, sharing a 2 megabyte L2. We have 4 clusters, and then we have a 4 megabyte L3 underneath those. That is exclusive with the cores. And then we also built cache coherency between these, but also we support full bandwidth IO coherent memory so that all the accelerator traffic can be IO coherent, and we can avoid cache flushing and all the goodness that comes with that. So our CPU, if we compare it to Parker, which was our previous generation Tegra SoC, we are at about 2x the performance. More for spec FP, but for spec 2K6, we're about 2x per core. It's 21 spec int 2K6, and then this is the aggregate. But yeah, the Xavier CPU is just the thing driving all of these accelerators. Let's talk about the GPU. So we looked at the Volta GPU, and the Volta GPU was designed to improve compute and deep learning performance. Now, unlike Volta, which is oftentimes used in a training environment and servers, right? Our GV100 is a big GPU. We looked at what do we need to optimize this for inference. So one of the things we did is we took the Tensor core, which is the core in our GPU for deep learning acceleration, and we added int8 support. And the int8 support runs at 2x the rate of the FP16. So we can do int8 even faster. And that is commonly used, as we've even heard today, in the deep learning inference space. We have faster cache accesses. That's part of the Volta core architecture we built. And in the end, this gets us 22.6 deep learning tops from the GPU. That's an int8. and over double the graphics performance. So then we looked at, as I talked about, the deep learning accelerator. We have 2 deep learning accelerators in the Xavier SoC. It provides not only it provides a second engine to run deep learning on, which is good for diversity, depending on, as I said. And then it provides 11.4 deep learning tops in int8 and half the rate of FP16. I don't want to spoil the talk tomorrow, so I'm not going to say anything more than that, but Franz is going to present on our DLA tomorrow. So our next engine I mentioned, Programmable Vision Accelerator. So this was a new core. We looked at what we needed for computer vision. There's a variety of filters, FFTs, Harris corner, all these different imaging algorithms. And we looked at how could we optimize sort of these filter loops and things in hardware to be extra efficient. And so what we did is we built this architecture. Each PVA is made up of an R5, ARM R5 core, and then 2 vector pipes. And each vector pipe has its own memory and DMA. In Xavier, we have 2 of these pipes. So let's talk a little about what is in the vector pipe. So the vector pipe is a 7-slot VLIW. 2 of those are scalar slots, 2 vector slots, and then 3 for memory. Now each vector unit, and I mentioned there's 2 vector units in each PVA and then two PVAs. Each vector unit is capable of 32 by 8-bit math instructions, 16 16-bit math, or 8 32-bit math vectors. So it's a 256-bit wide math pipe. Although on top of that, we do have additional guard bits for keeping the precision through the calculations. So it is a bit extended beyond that. But having those standard sizes helps with compiler targeting and things. Now, it's not just a vector pipe. We have a lot of secret sauce in there. We have hardware for table lookups, histograms. We can do hardware looping. So we have support to keep very high efficiency no matter what your filter size is. And so that's a lot of the secret sauce in PVA to make it very efficient. And then we have this DMA I mentioned. So PVA and the VPU is basically working on tiles of memory. And we have a DMA that handles most of the address calculations, the address offload, and keeps the unit fed as a side unit processing along the way. Feed the VLIW, there's an iCache, and as I mentioned, there's a vector memory there for local data. So, computer vision, right? We have all these pipes I mentioned. We can use them for diversity and also for removing work from the GPU. The GPU is great. A lot of code is being written for it. The goal is this stuff we know how to do well, some of these computer vision algorithms that have been around, let's move those off the GPU so that we can do all the new stuff we're doing on the GPU and still stay within our power envelopes, stay within our performance needs, and fit it on one chip. So what does this result in performance? So this is a little bit of a breakdown of mapping these different classes to our previous Parker SoC. So we have 2x the CPU. If you look at deep learning performance, we have 25x the DL tops, right? Parker had the GPU. We now have GPU plus DLA, and both with special deep learning math. If you look at sort of compute, we have sort of the ISP, PVA, and the CUDA on the GPU. If you add up those, we have about 12x the performance of what Parker had. If you instead add up the accelerators, we have a stereo and optical flow unit. We have lens distortion correction hardware. If you figure out the math, we have about 11x the performance on the accelerators. And then DRAM bandwidth, we have 2.3x the DRAM bandwidth. This is 256-bit LPDDR5, LP4X. Sorry. And so now some of you guys might be saying, well, we can't use all of that. Some of that's the GPU. Well, for Parker, most of these columns are the GPU. So here we actually have diverse hardware. We can use aspects of all of that at once to get a significant speed up over what we could do before. So then there's I/O. If you look at Parker, we built these various platforms for automotive and we have PCIe, but we looked at that and we said we can do better, right? That had PCIe Gen 2, we knew we could do better. And so we started off adding NVLink. NVLink on Xavier can support 20 gigabytes per second by each direction. It's IO coherent, and this is the link that we mainly use for between Xavier and the DGPU. That gives us a high bandwidth to an external DGPU when we want additional DL or compute horsepower. The next thing we did, PCIe, we built Gen 4. So 16 gigatransfers per second, Gen 4 controllers, and we support up to a by 8 lane width. So we have a variety of configurations, by 8, by 4, by 2, by 1. And not only did we add the usual root port, but we added an endpoint mode. The goal of the endpoint mode is that we can now take 2 Xavier chips, connect them together over PCIe, and communicate with each other. Before, that would have required an extra chip for us, a PCIe switch or something. So a lot of improvements there. We went to USB 3.1 Gen 2. Display, we added 4 display ports. So we have a high amount of display, 4K 60 support. And then camera. Camera, we have 16 CSI lanes, supporting up to 109 gigabits per second in C-Fi mode. We also support D-Fi. And so that's getting all of your camera and sensor data in. So a big improvement in the I/O subsystem, generational leaps in both PCI, USB, and adding NVLink. And that helps keep the system fed. So that's all great. Now the question is, when you get to a real system, how do I put all that together? What does it look like? How do I compare that really to what you guys had before? So I want to talk about autonomous vehicle use case, right? And of course, everyone's doing autonomous vehicle differently. So this is an example of how to think about autonomous vehicle. Now I'm comparing this to Drive PX2. Drive PX2 was Parker plus a Pascal GPU. And in this, we're comparing it to sort of one Parker, one Pascal GPU. So on Pascal and Parker, we basically had 2 things. We had the Parker ISP, we had the GPU, and 3 things, and then we had the CPU, right? Those were our main compute units we used. We didn't have, we had, of course, video decode, encode, but from a compute perspective, we didn't have a lot of additional blocks. And so if you look, most of the things map to the GPU. We have both the internal GPU and the external Pascal GPU. And so that was Parker. So now I look at Xavier, right? When we look at capture, meaning the camera coming in, and I map that to the hardware, we get the Xavier ISP. Same as the Parker ISP, improved with HDR, but the same mapping. Next, we go to image processing. Image processing is the processing of the camera. We have the Parker. On Parker, we would have used the ISP plus the GPU for some of that. Here we can do the ISP plus PVA. You also can use the GPU there if needed, but it provides additional hardware and frees up the GPU for other things. Next, we have perception. On perception, that we really view as a deep learning task in this use case. Now, different people do it different ways, but we're looking at it as a deep learning task, and there we previously had the GPU. Now we can augment that with the DLA and also the deep learning hardware in the GPU. So tracking and fusion, we just learned a lot about tracking and fusion. We can use the CUDA GPU there on Parker. Now we can do PVA. Again, we have this unit, stereo and optical flow. It's trying to generate those comparisons between 2 images that we can then post-process on PVA and do our optical flow and tracking. And so that hardware is very useful there, offloads a significant amount of horsepower off the GPU if you're doing that type of work. And then we have the GPU there. So along with that, we have localization. So localization is, again, figuring out where you are in the space. And that's an algorithm that has historically mapped to the GPU. And we can now map to PVA, and also the CUDA GPU can still be involved there. And then last, We have this sort of path planning. So path planning can be done in GPU and CPU, but our PVA also excels at certain aspects of path planning. And so depending on your algorithms, how you want to map it, it's there. Now, before I talked about 25x and 12x and 11x, trying to turn that into something more real, we mapped examples of this use case across this hardware, and Xavier can run up to 10x faster with this compared to Parker and a GPU. So we've taken this Parker and a big GPU, we've optimized bandwidth and other things and fit it into one Xavier SoC, and we can now do up to 10x the perf of what we would have been able to do before. So that's how we think about Xavier. Of course, we also think about Xavier in the context of the Pegasus on the right here, right? Some people may want even more. We've improved the I/O. We've improved the connectivity so we can do additional Xaviers attached. We can do DGPUs attached to Xavier. We also have our Drive Xavier platform, which applies to, gives you a Xavier-only platform, depending on your use case. And then we have a Jetson Xavier. Jetson Xavier is our embedded platform you can go buy. I think it was announced. I think it's going to be made available soon. I'm not sure when. But Jetson Xavier is our sort of embedded programming for the high-end robotics and drones and other things people are doing in space. It's the playground to play if you're not doing sort of the driving platform. So, and so that's Xavier, 10x the performance, all these innovations. And I would like to thank the entire team at Nvidia. 8,000 engineering years means most of the company was involved in different aspects of it. So I don't have a list, but I appreciate all of their input. Many of them are here today, and they all did a great job to make this a successful chip. So.
Thank you, Mike. So if you have questions, please come to the microphones. Looks like we have one over here.
Yeah, Bill Rash from Intel. I have a question on the memory bus. You show it as 256 bits. What kind of protection do you provide on the memory bus in case you get data errors on the bus?
We have ECC protection on the memory bus.
So it's more bits than you show as 256 bits then?
We have a way of implementing it through the memory bus shown. So we have an implementation of ECC through that memory bus.
Okay, thank you.
So any other questions? Yeah, well, thank you, Mike.